Much. That's a fun idea there that I must admit had never occurred to me. Okay, next up, wait a minute, he was sitting right, oh, he's moved over there. Scared me for a moment, thought we'd lost him. Duane Wessels, with a little bit of perspective from the top of the DNS tree. Or is that the root of the DNS tree? I get confused about that.
So I'm here to present some work that was done by myself and Jeff Sisson through DNS-OARC. I'm going to start with this picture that shows some historical trends in the contents of the root zone. This greenish line down here that's flat represents the number of TLDs in the root zone over the last 10 years. And this blue line represents the number of A glue records. The red is the number of NS records. Down here at the bottom is IPv6. The purple is the number of TLDs with V6 glue, and this orange color, which hopefully you can see, is the number of Quad A records. So something that's interesting is within the last year, we're sort of breaking away from the situation that there's been one Quad A per TLD. Now, having said all this, the purpose of the work that I'm going to present is not really to predict future growth trends, but more to analyze how will name servers sort of behave if the root zone is grown in certain ways. So it's sort of an interesting time to be a root zone because you're facing a lot of changes. Obviously, we have more and more IPv6 glue coming. DNSSEC is sort of right around the corner. We've heard yesterday about some schedules for when that will be signed. Most of us are probably aware of the proposals from ICANN to add new TLDs, and this probably represents the most significant amount of change to the root zone. Also, IDN names are sort of on the way. I heard at the RIPE meeting a couple weeks ago that we can expect to see on the order of 30 or more IDN TLD entries maybe by the end of the year. And there's other, of course, sort of constant pressures on the root zone, such as increased load and increased deployments of anycasted servers. So for this study, we were asked to look at 5 particular areas, 5 particular things that can be affected by changes to the root zone. First of all, just simply the size of the zone itself. Secondly was potential performance impacts, i.e. response latency. Third was how long does it take to start a name server loading the root zone or reloading the zone file. Next was bandwidth requirements for zone transfers. And finally, changes in response size as we expect larger DNS messages mainly because of signing. This slide has a few details about some of the hardware that we used. OARC has this very nice test bed that we sort of inherited from a National Science Foundation project. We've got 16 decent-sized servers, and with the specs listed here, and a couple of gigabit switches. In terms of software, we tested Bind 9.6 and NSD 3.2.1. Operating systems, for the most part, we used CentOS, although we did a few tests on FreeBSD. Some of the other tools that we used are DNSPerf, TCP Replay, NISTnet, and then quite a number of customized scripts and whatnot. So for the simulations, we came up with 5 different types of zone content. This table sort of on the left side here shows the labels that we use and then some brief descriptions. Sort of the simplest zone was an unsigned zone with mostly IPv4 glue. I say mostly because what we really did was we kept sort of the current ratio of IPv6 to IPv4 glue there. Next was, again, unsigned, but a zone where we had one quad A record for every A record. So as much IPv6 glue as IPv4 glue. The next three are signed zones. We had a signed zone with full IPv6 glue and 10% of TLDs having DS records, then 50% of TLDs having DS records, and finally 100% of TLDs having DS records. And I believe in all those cases we had 2 DS records per TLD. So then for each of these types of content, we had different sizes, ranging from 1,000 to 10 million TLDs in the zone file. So finally, some results. The first thing we looked at was memory usage. As the zone grows in these ways, how can you expect memory usage to change on the name servers? We use this utility called PMAP to report process size and also included shared memory and other sort of minor aspects of the memory usage. This graph shows for all of the sizes of zones and all of the types of zones how the memory usage increases. And as you can see, after some sort of in the larger sizes, it's very proportional. It's very linear. Down at the lower sizes, of course, you have some overheads from other things. But this is with bind. Here's the situation for NSD. They're if you cycle back and forth between these, they're quite similar. One thing to note, however, with NSD is our server that had 32 gigs of memory, that was not enough to load the 10 million TLD signed zones. So there's some data points missing there. Some pretty basic conclusions here. Memory usage is proportional to zone size. If you compared a fully signed, fully glued zone to an unsigned or a current zone, you would use about twice as much memory. And as I just mentioned, NSD needs a little bit more memory than we had to load the largest zone. The task 2 was to look at response latency. So here we crafted some PCAP files with DNS queries based on characteristics from our day in the life of the internet data, which was taken earlier this year. And then those queries were replayed with TCP replay. And in all cases, the queries were replayed at a constant rate of 5,000 per second. This graph shows the behavior of bind for an unsigned zone of the different sizes. The x-axis here is latency in milliseconds, measured sort of right at the name server itself. So how long did it take between the packet entering the box, or the query entering the box, and the response leaving the box? Obviously, in most cases, this latency is totally negligible because all the delays are going to be experienced in the wide area network, and 1 millisecond delay is really nothing to be too concerned about. One thing to notice about this is that the performance does not change at all, really, as the zone size increases. Here's the same graph with for NSD, and it's sort of similar. You can see a little bit of change, perhaps, as the zone gets larger. There's a slight lowering of these graphs, but for the most part, it's very consistent. And actually, NSD comes out with even slightly lower latency measurements. Here we're talking 0.1 milliseconds, so 100 microseconds. This is the graph for bind with the signed zone. And here we see something sort of interesting because it's no longer as consistent as it was before. For the larger zones, these histograms drop down significantly. The red and the green are the 1,000 and the 10,000. The blue and the purple are 100,000 and higher. And it's a little bit hard to see from this graph, so I also included a cumulative distribution function that shows, for example, this blue line is the 100K zone. Here's about, I think this is the 4-second cutoff, so it turns out that something like 70% or only 70% of queries are going answered within 4 seconds. And then, of course, as the zone gets bigger, it gets a little bit worse. Well, it gets worse. Here's NSD on signed zones. Much more consistent. Doesn't exhibit the same sort of problems. And also, I should note that here we have a 4.5 million TLD zone. I said before that we couldn't sign a 10 million zone, but we were able to sign a zone of this size, so we included it in this data. And here's the CDF for that. So, as I said, the bind performance is stable for all sizes of unsigned zones. For the signed zones, we see some degradation. This is a problem that ISC is already well aware of, and I believe they already have a fix in the 9.7 version of bind, which is currently in beta testing. And I have actually some more I'll explain a little bit more about this problem. NSD performance is stable, although we start to see some degradation at the largest zone that we were able to load. So I just want to explain a little bit about the performance problem we saw with bind and how this is sort of such a corner case, I guess. This problem only occurs when you use NSEC to sign your zone. It does not occur with NSEC 3. If you're not familiar with the differences between NSEC or NSEC 3, really you would use NSEC 3 if you were trying to sort of hide your zone contents. NSEC has a problem that it makes it easy to sort of walk your zone. And with a zone like the root, it's so sort of open anyway that there's no reason to hide anything. So NSEC will be used to sign the root zone. This problem only occurs with a zone like the root where it's likely to have a large number of glue owner names that get sorted in between the non-glue records. And that's kind of a mouthful, and I have an example of what that looks like on the next slide. This problem, only starts to become significant when we're talking a zone size of 100,000 or more. And there's no reason really to panic about this because we're sort of quite a ways away from any time where this could really be a problem for deployed root servers. So this slide shows an example of, this is some cut and paste of one of the zones that we used in the test. Here we have NS records for the COM zone and some other records. And then here, starting here, where if you can see the pointer, this is where we start to have some glue records, not necessarily for the COM zone, but these glue records end with .com, so they get sorted in between .com and whatever comes after it, in this case, Combaston. And for this zone, we had something like 10,000 of these types of glue records. So I believe the problem in bind was that there was some kind of linear search here that was not optimized enough, and so most other types of zones wouldn't have this kind of characteristic in them, so it should not be a problem. How am I doing on time? Okay. I'll speed up some of this. The third task was to measure start and reload times. These graphs are also sort of boring because lots of straight lines, lots of proportional behavior, but I included these tables just for fun. And you can see, for example, that when we start to get to zone sizes where it takes a little bit more than a second to load, you can see proportional behavior. So for this case, 100,000 TLD zone, it takes 8 seconds. For a 1 million zone, it takes 87 seconds, and the next size, it takes 950 seconds to load. And that's relatively consistent through all these zone sizes. And it's the same for reload times. Here's the data for NSD. Oh, I should also probably mention that we have some missing data here because, again, on our server with 32 gigs of RAM, that was not enough to do a reload for bind. Here's the data for NSD. Conclusions, everything here is proportional to the zone size. Task 4 was to look at the zone transfer characteristics, particularly bandwidth. This graph is a little bit complicated, so I'll try to explain it. On the x-axis here we have the size of the zone file on disk. And on the y-axis is the amount of data sent over the network for a zone transfer as a percentage of the zone size. So the 100% line is right here. This would be where it took exactly as much bandwidth to transfer the zone as it exists on the disk. These 4 clusters here represent 4 of the zone sizes that we tested, starting at 1,000 all the way up to 1 million. So these cases that are below the 100% mark are, well, the ones that are very far below are NSD. It turns out that NSD will do name compression in its zone transfers, whereas bind does not, I believe. So that sort of pushes bind up a little higher here. But you can see when you're talking about signed zones, which is these sort of higher clusters, it uses sort of a lot more bandwidth to do a zone transfer than it does, say, to do an rsync, you know, to just copy the bytes of the whole file. This graph is also relatively straightforward, but it shows zone transfer durations, how they change as you introduce latency and packet loss. So if you have no latency and no packet loss, you can do very fast zone transfers. But if you're talking about, say, 1% packet loss and a large zone, you know, it starts to become significant. I think I said most of this already, so I'm going to skip this. I'll talk a little bit about response sizes and TCP usage. So we wanted to look at to what extent will DNSSEC increase TCP at the roots. And this is a sort of a well-known problem, not really a well-known solution yet, but with DNSSEC the messages are going to get bigger, and we know that there are some clients that cannot accept these larger messages. This graph shows results of a simulation we did where the current root zone became signed, and we replayed some existing client traces that we had. And on these 2 nodes of LRoot, we got 0.3% of requests being retried as TCP. Well, that's not quite accurate. We had, these are replies that were truncated, i.e. the TC bit was set, and we would expect them to be retried as TCP. And this is kind of the same thing, except instead of the current zone, the green line represents what if you had a zone with 1 million TLDs in it. And there's an increase, again, in rates of truncation there. This graph shows the sizes of responses that got truncated. It shows the size if they wouldn't have been truncated, what would that size have been? So again, we replayed queries from our data where the DNSSEC bit was set and the EDNS buffer size was 512, and then we measured what would those responses be if the EDNS buffer size was not limited to 512. And there's a couple of peaks. One right here about 650, another one slightly over 700. I forget now which one of these is NX domains and the other is referrals. And then sort of the most that we saw was slightly more than 800 or right around 800 bytes. Okay. So from this we kind of concluded that the root servers can expect to see about an order of magnitude increase in TCP queries when the root becomes signed. And in the case of a root, it would go from say 5 TCPs per second to 50 TCPs per second. Increasing the number of TLDs appears to increase TCP traffic, and we sort of theorize that this is because certain names, like NSEC record names, get longer and sort of increase the size of responses. And then, as I said, UDP responses that might be truncated with a small buffer size would be smaller than 825 bytes if they didn't have to be truncated. So if you found any of this interesting at all, please feel free to read the whole report. It's it's a little bit long, and there's a lot more graphs in there if you like graphs. And also feel free to contact either one of us with questions about any of this. We're planning a follow-up study to work on some of the things that we didn't get to this time or things that were out of scope. So if you have any ideas for that, please get in touch with us. And that's it. If there's any questions. Also, I'm going to take your picture, so hold still. Thank you.
And thank you, Duane.